what they've done, what we're going to do today is wireless, is taken some of the material from the CCNA wireless and put it into the, on Friday we'll do automation. That's a brand new area. The wireless, there was always some wireless in the CCNA. There wasn't as much as there is now. We didn't get into the configuring of the wireless LAN controllers, which I hope to do this afternoon. But I'm probably not as much of the basic as we're going to do. But what we're going to do is start at the very basics of wireless and work our way up. So I hope that you have your pillow ready as we do these, because, you know, some of it's going to be like, okay, you didn't really need to tell me that part, but hopefully it's okay, it will now. The things that we're going to look at: wireless local area networks, managing the wireless LAN connections, and then we'll configure clients for the wireless LAN access. I've got a couple of wireless labs. One of them, and one of the objectives is to configure an autonomous access point. That's the one where you go into the with a web interface like you and I do at home and configure it, and then the wireless LAN controller, which we're going to configure multiple wireless devices at the same time. Those are the two labs, and they'll be late at the end of today. But the first topic is the wireless LAN fundamentals. And when we talk about wired versus wireless, as you get both of these up, the wired, we have two devices connected to each other. We can see that copper or fiber continuously end to end. It's called a bounded media. The physical properties of the wire, the 802.3, the Ethernet standard that we can use for these things. We don't have a whole lot of variables. We have copper or we have fiber. Copper, depending on whether it's twisted pair or coax, has a little bit of variation in the properties. The resistance is going to be a little bit different. The speed's going to be a little bit different over those, and that's why we can get in when we get into those. The twisted pair, the default, how far can you go answer is 100 meters unless we know something different. Coax, we could do a little bit different. The thick net coax, which is before the thin net coax, thick net used to be described as a frozen water hose, could go 500 meters for each Ethernet segment. The thin net, the kind of the more flexible with the B and C connectors, could go 180 meters, 10 base 5 and 10 base 2. And 10 being the key there, I guess, 10 megabits per second. We didn't go real fast on coax. But different variables, not so many as we're going to have with wireless. It's a bounded medium. The signal will travel over the cable path. It's going to be a fixed path. What's the issue with them? Not easily moved. You get a situation, you get a new a new boss in a certain area, and they want their desk moved from one wall to the other wall. Well, okay, now we got to go and move the drop for the network. And that's kind of a pain to do. So they're not that easily moved. And the way around that, oh, by the way, is when you do the initial installation, put a whole bunch of drops in. You don't have to have them connected. You don't have to have them run back to the NOC, to the switch that you're using, but have them available so that you can do that. So when you get a new boss that says, oh, I want to move the desk from here to here, that, okay, we can do that, move it around, and we can reconnect the computer by doing those things. The other thing that we would need to do, be sure you have a wire map. What's connected where? Because when you start troubleshooting and you have a wire problem, you got this office and so can't connect for whatever reason. Where's it go on the punch down block? What port on the switch is it connected to? So that you can now check for continuity, from end-to-end continuity, and you know where you're supposed to go. So wire maps, not one of the more glamorous things that are going to happen. Wire map is something that you need to do. Anyway, not easily moved. Compatible connector and media type, yeah, we got all of that. The smaller mobile devices, your phone, you can't plug it in. Your tablet, you can't plug it in when we look at those things. So they're going to have to be wireless. The wireless, untethered from the wire, at least from the user standpoint, untethered from the wire, untethered from the device. We still have a layer 1. The layer 1 happens to be the atmosphere that we use in the wireless instead of the copper or the fiber, the copper or the glass when we do these things. Convenience and mobility are what we have with these things. You know, you can take your phone and move around, drive around. You can use it as a GPS. You can log in at the grocery store. You can log in or connect it at the grocery store, usually an open. You can connect it at the Starbucks or at the McDonald's or wherever else you are. Your tablet you can connect and have internet access. You're not going to take your desktop, even if it's a one piece, and connect it in at McDonald's when you do that. So the convenience and the mobility. The problem is going to be security. And a lot of different devices are going to be on the wireless. Wireless has become, you know, one of the preferred, and I don't know, you guys may be on wireless. My desktop that I'm using for this, I'm wired. I've got a laptop in here that is on wireless. We've got tablets that are on wireless. We've got televisions that are on wireless. I had them set up on a Powerline NIC for a while, but the wireless works just as well, and don't have to fool around with it. Don't have to worry about it. So what are we going to do? How are we going to do it? And I told you about when we got Friday afternoon, and all you networkers that have been networkers know that Friday afternoon is when they all happen. Oh yeah, we just thought of this, that, you know, on Monday we have this new room that we're going to have to put students in. We got a class starting in here, 30 workstations, that we need connected to the network. And oh, by the way, you got to get it done this weekend. So not a piece of wire in the room. So nothing run to it. We could spend the entire weekend doing a wired connection, and the wired connection would be from the switch to each of the individual devices. Or temporarily, we could run a piece of wire from the NOC to a wireless access point of some sort, and then use the wireless NICs. And we were fortunate that these computers did come with wireless NICs. They were external NICs, oh, by the way, just as a curiosity thing. But we had wireless NICs that we could set the room up pretty quickly. So the convenience, the mobility that goes on with these things. Lots of different devices are going to connect to the wireless. We can have our phone, we can have our tablet, we can have our televisions, we can have our step counters. All those things are using a wireless of some type. Many types travels through the air, through space. And that means that we're going to have a lot of different variables that go on. Atmospherics. It's raining right now. Anybody that's using if you're raining, we got thunderstorms in different areas. You got one here that says, you know, lights flickered for a minute but came back. Yeah, and those things happen. But if you've ever used like satellite television, or if you're using satellite television, what happens to it in a thunderstorm? It just goes away. What about in a heavy fog? It becomes a problem. One of the atmospherics, one of the things, and I did a wireless security course one time, and the book said, you know, you set up this auditorium that they're going to have a lot of presentations in, and we set up the wireless network, and it works just absolutely spectacularly. And then it gets filled up with people and doesn't work so good anymore. What happens? Well, water absorbs the wireless signals pretty quickly, and we humans are, well, something like a whole big percentage. I want to say a number. We're mostly water, so we're going to absorb a lot of those signals. They travel through space. Lots of different things, and we'll talk about them. We'll have a slide on the things that can interfere with it. Got to adhere to the 802.11 standard. 802.11 A, B, G, and we got now AC and AX, the different standards that are available. This is another thing that in the early days, we didn't have any real standards. If you wanted to connect wireless, you had to go get the same wireless access point, wireless router, the same wireless NIC on down the line. And now just about everything, including this desktop that I have, comes with a wireless NIC in it. so that we can connect it. And we have standards to allow us to go by whichever manufacturer of wireless access point, wireless router that we want to do. The coverage exists in an area where the devices are expected to use it, we hope anyway. The coverage in areas that are hard to wire or power. And the power we're talking about, power over Ethernet, the wireless access points, can be, frequently are, wireless over access point things that we're going to use. The topologies that we have in here, the wireless communicates in free space, obviously. One device, and these are just two sending together. One device sends an RF signal to the other device, radio frequency signals. And yeah, we can do that. This is showing a one-way. We have a transmitter and a receiver, and we only have two devices. And yeah, this is not something that we're really going to want. They got to be on the same frequency. They have to use the same scheme. They've got to use the same protocol. We have to do lots of configuration in order to have these guys talk to each other. This is simple, but not practical because we have two devices. And you know, we would call this, and we'll call this a little later, an ad hoc, when we want to just set these two devices up. We need two-way communication, so we need each of them to have a transmitter and each of them to have a receiver. The issue that we get into with these is we're on the same frequency, we're using the same scheme, so if we're doing that, we can only transmit or receive. These are going to be a half duplex configuration. So wireless is in fact half. Transmitter and receiver on each of these things. Now we can communicate back and forth, have two-way, but it's going to be slower than the wired because of that. Each has to take its own turn. If we have a lot of different signals, then they're going to start interfering with each other. Who is going to be able to send where, and then one's going to override the other. This signal's going to be stronger. This is going to knock the one off of the communication, one to the other. We need something that the more devices, the greater the probability we're going to have of interference with these things. And we can't transmit and receive at the same time. So these are going to be half duplex configurations. The most basic level, there is no inherent organization. And so we're going to start at the bottom and work our way up. So we're at the very basic way that we could use communication. You know, and I don't know, when I was a kid, you know, we would set these things up, we would do these things. We really did have the two tin cans on a string, which, you know, kind of maybe sort of worked. And that's what we're talking about here, a really basic two computers, two tin cans on a string, two computers talking to each other. We put the other devices in here. They're all going to interfere with each other. So we're going to probably wind up with nobody being able. The first solution, or the solution, not the first solution, but the basic service set is to make every wireless area a closed group. And we're going to advertise the capabilities, and we're going to grant permissions. And that's what we do with these things. The standard calls it a basic service set. At its heart, it's an access point, and that's what we're going to call an access point or a wireless router when we do these things. Offers the services that can create an infrastructure, and yeah, you guessed it, you're going to get stuck with looking at a Wireshark before we go any further about what goes on in this wireless communication. Establishes the basic service set, advertises its capabilities and those sorts of things. When we look at these things, and we're going to refer to these things, we have a length here, not a whole lot. We have a beacon frame here, flags that go on. We look down here in the beacon frame, the frame control field that goes through it, the destination address, broadcast, the receiver address here is a broadcast. The Netgear is the device that is there. The IEEE 802.11 wireless management, fixed parameters, the time state, the beacon interval, and these things are pretty fast here, every tenth of a second. Things, the tag parameters, and the tag parameters, the SSID here, and it has an SSID. That makes it easier for us. The basic service set is real basic, is basically a MAC address. We then overlay this SSID over the MAC address in order to make it more convenient for us to be able to find what we're looking for. And then the supported data rates. What does it support? The data rates that it supports all down the line. The supported rates, one to the other. The DS parameters, the traffic map that goes on, ERP information, extended supported data rates, vendor specific. This one is Broadcom, and then the vendor specific Microsoft. The Cipher suite that we have that goes through these things, the authentication key management. And this is just in the beacon frame. What we have, what are we going to do? We have to tell, or the basic service set, the advertises its capabilities for these things. Beacon frame after beacon frame after beacon frame that goes on. So we have an awful lot of information. And then even up here, let's look at the radio information, the PHY, the physical, and at the physical layer, we're always going to have a PHY physical component of this thing, 802.11b for this thing, short preamble. Channel 11, signal strength that goes on, a duration for it, and then we go into the beacon frames. Not showing you this that you got to know. I'm just showing you this that hey, there's a whole lot goes into this wireless communication of the wireless devices themselves, and I think for the price, they're pretty amazing little devices that you send out all that, you have all that communication, and we still now can get pretty fast when we do these things. We're into gigabit frequency when we go into the AC standard. At its heart, it's an access point. The basic service status establishes the BSS over a channel when we do these things. And here the SSID, the BSSID is the MAC address. The SSID is the name that we use that reflects maybe the purpose that goes on, so that people can know where to connect, what we're going to connect to. Because if we were advertising, the SSIDs wouldn't make a whole lot of sense to users. My network, get your virus here, whatever you want to call it. That's what's going to be broadcast. And you saw that it is broadcast in the beacon frame. We can tell the system not to broadcast that, and that will happen. It won't show up to the regular user, but anybody that's using, in this case, a Linux machine, because the only way to put a wireless NIC into promiscuous mode is to use Linux. Windows won't do it to be able to see all of the information. But you're always going to be able to see the SSID from a promiscuous scan if you want it. Bounded by area, APs, the signal is usable and the cell is in the shaded area. Where can we go? And this is showing a nice circle, and that's probably not going to happen for real, because we're going to have all sorts of different things that are going to modify, bend, reflect, absorb the signal that goes on. The cell shape depends upon the antenna. This one is representing an omnidirectional antenna. We can have a directional antenna, and I tend to try to cover everything in the first few slides, and we'll do some other things again. But when you see how far can we go with these things, we're going to have a directional antenna and an omnidirectional. Omnidirectional goes in all of the directions. Think about these things as when the signal gets on the antenna, there is a certain amount of power that's available to it. In the Omni, it goes out in all directions. If we focus it with a directional antenna, we now concentrate that same amount of power in a smaller area. And that's one of the reasons that the directional antennas are going to have a greater distance than the omnidirectional antennas. And the distances that we talk about, these things are all going to be in perfect circumstance too. No impedance, an open field, great atmospherics, no absorption of the signal that goes on. A single point of contact for every device when we do these things, and it advertises the BSS, uses a unique BSS ID based upon the MAC address of the wireless access point. This is like switching, similar to switching in a wired network, and it also uses the SSID for the text advertisement. Once we get a membership in this thing, once we get it's called an association, once we get connected to it, the membership in it, we're going to have an association. We're going to be associated with that particular wireless access point. And we at home use wireless routers. The wireless access point, the picture here, there's no routing capability. If you want to make your wireless router a wireless access point, you can do it. Just use the switch ports to connect one to the other and turn the DHCP server off, and you can make it a wireless access point. Don't use the WAN. Why would you do that? It extends the wired network. At some point in this thing, at some point this device, because it's got all these wireless devices connected, if we're going to make it useful on our network, we're going to have a wire going back to the wired network. So what we're using here, just like I talk about in the room that we had to set up, we're extending our wired network using a wireless configuration, wireless devices. The SSID is familiar to the wireless users. That's what we use, the my network, your network, somebody's network, Joe's network, whoever is going on. And I've got one around here that I haven't seen it lately, so maybe they finally figured it out in that advertising. It was new thermostat. Okay, why would you want to advertise that? So somebody can now try to break into your system. And the reason I say that is Home Depot had a major breach a few years ago. Some of you may have been caught up in it. Got a bunch of credit cards. How did they get into it? Through the environmental controls. Some air conditioner tech lost control of his password. So we now have a foothold on the network to get so familiar to the wireless users, as opposed to the BSSID, the words that we use, the names for the Wi-Fi networks that we're going to use with these things, and the wireless devices detect and display the names of the networks. You've seen that, been there, done that with those things. Broadcast can be shut off. We may or may not require a password to connect to these things. We have open, and the open authentication, and it's still open. It's still an authentication. It's just that we don't have to put in a password. Open authentication is the default for these things. So over here, the mobile station sends a probe request, and then we have the probe response, the probes that we have in these things. Authentication for the sequence that goes back and forth. The association request, and then the association response. After all of those steps take place, then we can start the data. The distribution system, after we're granted association, the device becomes a station, an STA, which is the designation, I guess, that we're going to see for these things. Most communications to and from the client passes through the access point. Most, like all of it, is going to pass through the access point, unless we set up, an ad hoc. The data frames are relayed through the AP, and if no direct communication, we don't have any control for these things. Direct communication to the device itself. Standalone network. We eventually want to communicate with other devices and an access point that can uplink into the Ethernet network, and the 802.11 portion is called the distribution system. Access point is a translation bridge. That's the other thing that's pretty neat about these things. Translation bridge maps the VLANs to an SSID. Will do that. If we have multiple SSIDs, and we will, in the devices that we're talking about, be able to have multiple SSIDs on an individual access point. Yours at home probably has that capability now. The new ones, the older ones didn't. The new ones now have, you've got your network, and then you've got a guest network. Those are two different SSIDs with two different capabilities. The guest network is outside of your private network. Users that connect to the guest network can't access resources on your private internal network. So multiple SSIDs, multiple BSSIDs, we can do these things. So what we want to be able to do, the translation bridge, the other translation it does is wireless to wired, and I really think that's pretty good there, because we use different sorts of connectivity for wireless than wired. We use CSMA CD, and then this one you're going to use CSMA CA in order to do. The AP is the access point is a translation bridge. It's going to map VLANs to SSIDs, and that's where we're going to get the power or the leverage of these things, so that we can now have different users. We can have students, we can have faculty, we can have bosses, admin, whatever, that will connect to different SSIDs, and we're going to have different ways to do that, either the pre-shared key or use a radius server, so that we can have usernames and passwords that are associated with each of the SSIDs, and once they connect to the SSID, they get an IP address on a particular VLAN. And that goes back to what we have here. We are eventually going to need to connect back to our wired network. In this one here, maps VLAN 10 to SSID My Network. We can have multiple VLANs that would be available on this network. It appears to have multiple connections. I guess we fooled you, fool me, fool you, fool whoever. Yes, we have the multiple SSIDs, but you notice that we only have one wired connection, so the speed's not going to increase. Each of these is going to share those. We're going to have one radio back here. These guys look like they're all on different frequencies. They're not. They're all going to be on the same frequency, the same radio to do these things. And you notice the progression over here of the BSSIDs, the basic service set identifiers, the MAC addresses. The first portion of it is going to be the same, and we've seen similar concepts with these things, and then 21, 22, and 23, and that's going to be a typical progression of these things. The clients are going to use the appropriate SSID. Once they connect to the SSID, it's going to be mapped to a VLAN, and golly, we have a trunk here. The trunk port allows all of the VLANs, all the communications here, the VLANs 10, 20, and 30, to go back and forth from these things, to allow us to go from one to the other. And again, over here, the last digit of the MAC address, the multiple VLANs, the multiple SSIDs, BSSIDs, MAC addresses, usually accomplished just by incrementing the last digit of the MAC address. Multiple VLANs, limited area, all going to use the same channel, the same frequency, the same communication. So if we get too many of these things still, and there is a limit, and each of the devices is going to be different. I've always kind of looked at around 25 or 30 devices before you start overloading. Each of them is going to have a specification, and you can look at the specifications for the device, should get an idea of how many of these things that we can have, how many we can have connected to them. But here we've got an SSID, my network, your network, and the guest network. Remember, all of them are going to be using the same channel. They're all going to be using the same transceiver concept. They're all going to be using the same broadcast, the same transmit and receive frequency. And we are in half duplex. We can transmit, we can receive, but we can only do one at a time. And as we go a little bit further, we're going to look at some other methodologies that allows us to do that. They all sharing the same hardware, bounded by the same geography, which means that, in your house, they have the same signal strength regardless of which one you're on. If you're in an enterprise, you're going to have the same signal strength regardless of what you're on. And users may not be set up that way. You may have different signal strength for different users to do that. That's why we're probably going to want to have multiple devices. And that's where we get into with the extended service set. One access point probably is going to be insufficient unless you got a relatively small area, probably like your house. Even in my house, I found that it's not really all that sufficient because of some of the obstructions. I've got a television in the basement. The access point, the router is behind me in this room. So on this floor, not a real problem. Everything works really well. Going to the basement, got to go through the wall to get out of the room, through the floor to get there, and then the television's on the other side of a brick fireplace chimney. So it doesn't work out so real well. What I wound up doing was buying one of the wireless repeaters, putting it into where it has an open connection with the access point here, and then an open connection to the television itself. It works pretty well when you do those things. But the extended service set, I guess I digress. Extended service set, we need more access points for different geographic areas, different floors, different parts of maybe a warehouse. One of the things that will happen with this is in a warehouse, the fork driver, the guy that's getting the stuff out, getting it ready to ship, bringing it to you to go from one to the other, and then when it comes in on the truck, a whole bunch of them is putting it away, needs to get information and needs to send information. So one access point may be inadequate because these places are really big and they've got impediments in the way that's going to prevent the signals from going around. So more than one access point. And again, here we have VLAN 10. We're now going to send VLAN 10 the BSSIDs for these things, and each of them are different, but the SSID is going to be the same. So what we can do is on each of these, and these are wireless access points, and these are going to be lightweight access points because we are going to configure them centrally to do this. Or if you're a glutton for punishment, you can go to 300 of them and configure them individually and map the BSSID to the SSID. And then we won't get a map. Well, actually, BSSID, SSID, and then we're going to map them to VLANs. What this is showing here is the ability to go from one to the other. And once we configure it to do that, roaming is what the term, and probably nothing magic about roaming. But roaming is a configuration that has to take place. We have to configure roaming. We could always go from one to the other when we do that. But if we didn't have roaming configured, we'd actually drop the connection from this one and then reinstitute the connection over here, and we'd kind of start over with what we were doing. We really don't want to do that. In roaming, the controller, which isn't shown here, what we do is pass the connection from one to the other, so that when you go from one of these areas, from the BSS1 to BSS2, the connection gets passed from one to the other. You get the same IP address, the same TCP/IP, the same SYN/SYNAC/ACK. You don't have to go through that process again to reestablish the connection. It gets passed from one to the other. Wireless devices will always tend to connect to the strongest signal. And this is what hackers leverage when they want to put in an access point and have us connect to it, a rogue access point. You're going to put one in, maybe it's got a stronger signal strength or closer to the device that you're trying to get to connect to you, because wireless will tend to connect to whatever the strongest signal is to it. So we add more access points in the geographic area when we do these things. Interconnected with the switched infrastructure, and then we're going to associate with the AP that is physically near the one that actually has the strongest signal. Moves to the nearest switch to it, and this is the roaming process. And again, roaming is something that really does have to be set up. Yeah, we can go from one to the other and connect to the strongest and do all that other stuff. But until roaming is configured where it actually hands the connection off from one device to the other, then we're just connecting to the strongest signal. The independent basic service set, this is the ad hoc. Where the impromptu situation, we need to connect two wireless devices together, so we set it up, one connects to the other. It's going to be called an ad hoc connection. We do that. It's a wireless to wireless connection. You can do that, connect one wireless NIC to the other wireless NIC. Transceivers are going to transmit and receive. We don't really have a control mechanism in here to allow other users to get into doing the connections. Wireless local area networks connect to the local area network or the internet without a physical media, a bounded media. This is unbounded media. So in this, exactly what we talked about a little earlier, I think when we do these things, we have all these wireless devices connecting to the wireless access point, but at some point in the chain here, we have a wired connection that's going to go back to a wired switch. It goes back to our wired network to allow us to get the resources that we need to communicate. And then the next is we use RF communications, often implemented with the existing local area network. Why do we want wireless? We're extending our network. We're extending our wired network so that we can have more users, or users at a further distance, or users that are in a place that it's difficult to put wire in, or users that are in a place that we can't put wire in order to allow them to connect on our wired network. With that, we're up to, and I think what I want to do, so we'll look at some other wireless topology. I already kind of have referred to this one. The repeater extends the range of the access point. So we have the access point going to the switch, and the one on the left there is a layer 3 switch that shows it connected to and then we have a repeater that is going to extend the range. The repeater that I put in works pretty well, but when you think about it, we have the same frequency, got to have two channels, two to transmit, two to receive. The more sophisticated protocols that we have now allow multiple connections, but typically we're going to have a single connection. So what this says, we need the two frequencies here in order to communicate with one to the other. We're going to need, let's say here, the pink frequency to go to the repeater, and maybe here we'll have the black frequency to go to the device, so that they're not interfering with each other, because they obviously are within range that they could overwrite one to the other. If we had a single frequency to do this, then we would go to here to this one, and then we would go on back. We're going to decrease the data rate by like half, because we send it to the repeater then sends it to the device. They can only connect one to the other. If we have different frequencies, two channels here, two to the transmit, to the receive, then we can have both of them functioning. We have a work group bridge, and this thing, two types of work group bridge. The universal is a single wired device, can be bridged to a wireless network. And remember, a bridge is going to create connection from one to the other. Going to have some other images here of what can go on with these things. Or we can have a work group bridge. But what we're really talking about when we talk about bridging with these things is we have a wireless access point here, wireless access point here, configured in bridge mode. And it's going to be one of the modes that we can have in bridge mode. And back here, we're going to go to our wired device. And back here, we're going to go to our wired devices. This is then going to allow these networks, these segments, to communicate with each other through an area that we can't put wired in. Maybe they're in different buildings across the street from each other. The city doesn't like for you to pull wire across the street, those sorts of things. So we can now use a wireless connection in order to do that, to connect one to the other. So the wireless, the Workgroup Bridge, Cisco proprietary implementation that allows multiple wired devices to be bridged to a wireless when we want. The point-to-point outdoor bridge, and this might be something, this is kind of more like the one that we were talking about. When we get these devices to different buildings, and we're showing here a parabolic antenna, a focused antenna that's going to be a stronger signal strength or power level than we would have, obviously, than with our rubber ducky. Rubber duckies is the little antennas that you used to be able to see on the wireless access points, not so much anymore because they make them internal, so you really can't tell how many antennas there are. But when we look at these things, we're going to have a higher power capability for these things, and it's going to be, again, it's going to be more focused and much more focused, where we take the energy that's available, instead of spreading it out 360 degrees, we're going to focus it as much as possible from one to the other. 2, local area networks need to be bridged across a distance here, the point-to-point outdoor bridge, and at each end has an access point configured in bridge mode. When we do these things, special purpose antennas focus the signals and it maximizes the link. We may have something in the middle of the point-to-multi-point outdoor bridge, central site. In the central site, they're going to say it's got an omnidirectional antenna. It may or may not be omni. It may be focused in each direction. Keep in mind, if it's omni, it's going to go 360 degrees, and you may or may not want that to happen. For those to happen. Central site bridge to several other sites. The central site has an omnidirectional or maybe a specialized antenna in order. The edge sites here have directional antennas. You guys that have worked with radar, that's exactly what we do, is the parabolic antennas like this, because when the little bitty signal gets back, we focus it in so that the maximum signal gets focused into the feed horn. Feed horn return signal comes back in, sends the signal in and out. So reflected is going to be a very small signal when it comes back. These parabolics are going to help to focus the signal and amplify the signal that we have with these things. The wireless mesh network, and Cisco has devices that we can set up a mesh. Actually, you just put in the wireless devices and they'll figure out who else is connected. Multiple access points are going to be configured in mesh mode in order to do this, and the wireless traffic is bridged from one access point to the other. It's going to be a daisy chain in these things. The basic service set is going to be 2.4 gig, and the AP to AP is over 5 gig. This is one that we talked about a little earlier. Yeah, we need 2 frequencies. We've got 2 frequencies here. That the access points are going to be connecting to or talking to each other, relaying the information over the 5 gig frequency range, and the connecting to the access points. The devices are going to be using the 2.4 gig range. The carrier signal, and we kind of looked at this in Ethernet, but carrier signal here, the carrier signal is just a constantly changing frequency or constantly changing signal. No real interruption of either the frequency or the phase or the amplitude of these things. The modulating signal is the data that we're going to put on it, the intelligence that we want to put on the carrier signal, and then the phase modulated signal is down there below. Phase is the starting and the ending points of these things. So we have these, and it could be frequency, it could be frequency modulation, it could be amplitude modulation or phase modulation. What we use in the wireless is the phase modulation, and phase is the starting and ending points of these things. If we have a signal like this, and a different signal starting and ending, they will be in phase or out of phase, and these are going to be out of phase, and I probably drew that poorly, but it'll be shifted from one to the other, and that's where we get the change here in the signal, the phase of what goes on, the starting and the ending point of the individual cycle. And a cycle per second, a cycle is one complete up, down, around, one complete for that, but one complete path. The starting point to the high point, back through the starting point, low point to the starting point, one to the other. This is a single cycle. Probably nothing that you haven't seen before, but cycle and phase, frequency, how many changes per second, amplitude modulation, how far up and down we go. Frequency modulation and phase modulation really are not subject to noise, or are as subject to noise as would be an amplitude modulation. If we had amplitude modulation and we get a lightning strike, it's going to put noise up here, so it's going to change the amplitude. That's where you get the noise with these things. If we had a frequency or a phase modulation, we get this. What they do is then they truncate the signal, so they'll chop it off, because we're not worried about how high it goes. We're just worried about the changes per second, or what happens here in the compression and the spreading out of the signal itself. So the noise can actually be chopped off. So that's what makes, if you listen to FM radio, makes it so that you can hear it. If you ever listen to AM radio in a lightning storm, and you can't listen to the AM for these things. So we have the electric and the magnetic waves that go along with these things, and they're going to be at 90 degrees to each other. The waves travel and are always at right angles to each other. The right hand rule, and as I recall, is you take your right hand, you wrap it around the wire, you're going to get the direction of the fields themselves. Just something that is, I think, more of an interest item, that we do have these electric fields. We have an electric component and a magnetic component of it, and this is what a signal might look like that actually goes on one of these things with the modulation that we would have with it. Electromagnetic waves, they're not going to travel in a straight line. Travel expanding in all directions away from the antenna. And that's with the omnidirectional antenna when we do these things. We'll put this up. So the cycle we talked about a little earlier, from the 0 point through the 0 point and back to it, to do these things. But they're going to spread out in all directions when we do those things, when we talk about it. And the equal or omnidirectional equal sharing of the power maybe or may not be something that we really want to do when we do that. If we need a better, more focused, we can have focused antennas. There are a bunch of them out there. One of the ones, if you want to look at something that's kind of interesting, is go to YouTube and look up the Pringles can antenna for wireless. You can make your own if you want to do that. Omnidirectional, spreads the signal in all directions, equal signal strength in all directions, as this one shows. If we use one of the directional antennas, we're going to have the power focused in a much narrower beam, and then we're going to have a greater distance. The frequency spectrum that we use, and this is here so that you can see, where are we in this wireless world, in the frequencies that we have. So we have it here, the microwave and radar. This is where our 5 gig and our 2.4 gig are going to fall in here. We got a gig here, and then the 10 gig, it's going to fall in the microwave and radar. Microwave here, probably one of the things that we want to think about, because microwave ovens are going to interfere. The wireless bands are the 2.4 gig, and then in the 5 gig we have multiple bands that are available. The 2.4 gig, and we'll look at them in a little bit, really only has three clear channels that you can use down here. Television, FM, shortwave, what goes on, and we have sound that we use in subsonic. The thing that happens also, the higher the frequency, the shorter it's going to happen. So 5 gig is going to not go as far as the 2.4 gig. In the world of, I guess, Navy communication, submarines use this thing called ELF, extremely low frequency, in order to be able to contact them while they're underwater. You can't really send a whole lot of information because the data rate gets really slow. And you say, why would that be? And I guess I jump around a lot, but when we're putting data on these things, if I have something like this or something like this, I can put more data on this because I have more changes per second. If I have something like this, I can't put a whole lot of data on it. So basically what they do with that is to send them a signal in the extremely low frequency, and then they'll go on a different frequency, different antenna in order to communicate. So why does that become an issue? Back to the absorption. The higher the frequency, the greater absorption in water. The higher the frequency, the shorter the range. The higher frequencies, in this case, we have more of them in the wireless that we have, but we're going to have a shorter range, higher data rate. Higher data rate. When we started these things out, this one was 54, and we'll have all this stuff again. 54 megabits per second, and these were, 10 megabits per second? I think we eventually got to 54 here. Now we are up to 600 with the 802.11n, and 2 or 3 gig with the 802.11ac when we do these things. So the 5 gigahertz range and the 2.4 gigahertz range are the two ranges that are unregulated. And unregulated is a key here, because unregulated means that nobody's controlling what goes on. So if somebody puts something in your frequency range, you can't do anything about it because it's unlicensed, unregulated. It's available to whoever wants to use it. I'm doing a course sometime, and the guy was saying that, hey, we had this parabolic antenna. We were connected to another building, and all of a sudden it quit working, and he goes up on the roof and somebody put an antenna in front of his antenna. Can't do anything about it because it's an unregulated frequency range. Both of them are unregulated frequency ranges. So the wireless bands, the 5 gig and the 2.4 gig. The 2.4 gig is the one that we use a lot, have used a lot. When you look at it and say, hey, I've got all these, 0 or 1 through 13 for the channels, 1 through 12, I think is what we use in the U.S. But channel 1 here, the problem with it is we need a bigger bandwidth here. We need these things, and I think in probably about 20 megahertz. And the channels don't go 20 megahertz. With 2412, we got 5. So if we go here from the 427 to 447 would be 20. Yeah, it is right here. It says 20 megahertz. 20 megahertz for these. We only have 3 clear channels, 1, 6. When you look at your wireless, if you've got your neighbors, and we got one of our neighbors which kind of gets in the way, it's far enough away that it doesn't really interfere. It's low signal strength, so that is overcomable. You really want these guys 1, 6, and 11, and you want to be as far away from everybody else as possible. What that means is when you're setting up multiple access points, if we have, let's say, an access point here, an access point here, and one here, what we would want is to go to 1, 6, 11, and then we do another one, we go back to 1. You want to be as far away as possible. You don't want the channels to be able to communicate with each other, to interrupt each other. So 3 clear channels in the 2.4 gig. 5, not really an issue. Each of the 5 gigs are going to be clear. So there are more frequencies. It's going to be a higher data rate, shorter distance because of all of the atmospheric interferences that go along with it. Higher frequency, high frequency, low data rate. Low frequency, lower frequency, lower data rate, greater distance. Get the signal from one location to the other location. 14 channels, too much overlap. We don't use 14 in the U.S. I guess 1 through 13 we use. 14, the Europeans use it and Japan uses it. There are some others, but we only use this range where the grays are here. 14 gets a little bit better offset than the rest, but it's still going to have some overlap. And again, the 5 gig doesn't have any overlap. The wireless signals, a couple of things here, the radiation pattern that we have with each of these things, the overlap and where do we go, or how do we arrange these things. And I've got this thing up here that the inverse square law. The strength is equal to the inverse of the square of the distance. Well, that makes a whole lot of sense. What that really says is if we move a device twice as far from the source, we're going to have a quarter of the power. So if we go from 50 meters to 100 meters or 10 meters to 20 meters, we're going to have 25% or a quarter of the power that we had at the original location. The farther from the source, the slower the data rate's going to be. And that is one of the characteristics of wireless. The weaker the signal, the slower it's going to go for these things. And when we do the calculations, the great speeds that we advertise, it's based on a pretty close system, unencumbered. How far can we go? No kinds of interferences in the system, no walls, no other RFI radio frequency interferences, those sorts of things. The barriers to the signals, they'll interfere with each other, so we need to use different channels, and then EMI, other interferences, EMI, electromagnetic interference. Microwaves are a big thing. Used to have these the questions, practice questions anyway, that people in the break room are complaining that the wireless quits working intermittently at lunchtime. What's the problem? Well, people are using the microwave, and the wireless access point's too close to it. I had a student one time said, "Oh, my wireless isn't real good. And, you have any kind of things?" I said, "Oh, you're sitting on top of the refrigerator under a fluorescent light." Fluorescent lights are not a constant light; they're constantly going on and off. So, and the refrigerator with the compressor, the other things, machinery that can interfere with the signal. You need to be aware of all of those things and try to get it as far away from any kind of interferences as possible. And the closer we are, the better it's going to be for each of these things. The radio broadcasts themselves, the wireless local area networks transmit the signals through the air via RF frequencies. Yes, we've been there, got that, said that multiple times. It's an unbounded media. The antenna determines how focused it's going to be. And, from the omnidirectional to the directional antennas that we can use. The directional antennas, something like this, that we're going to have a cone in here. It's still going to spread out some from this cone. When we get the signal back, it's going to then be focused to a point to allow the maximum signal available. Antenna theory is a whole study unto itself. We can get amplification from the antenna depending on how it is configured. We can also have other issues with the antennas and with the wires. If the wire length is wrong, and we have something comes in here, and I'll try to make it quit, we can actually shut down our signal if it's what's called a quarter wave shorted stub, or quarter wave length in here will stop, and that can probably be at the top, would stop the signal. Different things, different issues are going to happen with all of the wireless, and with the signals. Antenna that we use can all affect what goes on in the wire. The wire and the wireless share a lot of similarities. They use the same layer 3 protocol. Once we get above layer 2, and I've probably said this a couple of times, multiple times, once we get above layer 2, everything's the same. The data link layer is where we define the the WANs, the LANs, the wirelesses, and the wired, and all of the other different connectivities, and IP addresses, and IP addresses, and IP addresses. So we're going to use the same layer 3 protocols for all of these things. The nature of the atmosphere makes the wireless different from the wired. The wired's going to be consistent when we get it connected up. The characteristics of the wire aren't really going to change. The characteristics of the atmosphere can and will change on a regular basis. The wireless interferences, and these are probably, let me just open all of these up, not anything that's really earth-shattering, I guess, but physical objects are the most common. The density of the material determines the ability of the RF signal to pass through and still maintain adequate coverage. If you have a cement wall with rebar in it, probably not going to go through there. We had one of those. We had to find a method in order to get the wireless signal into the area, and it was one of those. We have this wall here, bigger obviously, and we have this room back in this area here, and there is a door here. So what we did was set up a wireless access point so it can actually go through the door to get beyond the rebar. Back here, to get the wireless back into this area, had to figure out a path in order to get there. The density determines the ability to pass it through and maintain coverage. The walls in our house, yeah, we're probably going to have not a real big problem getting it through, but again, the cement walls down here, concrete and steel, particularly difficult to pass it through. Radio frequency interference, RFI. What other devices? Cordless phones, not cell phones. Cordless phones, the old cordless phones that we would use. Microwaves are going to be running here. Wireless controllers run at 2.4 gig. Bluetooth is 2.4 gig. A lot of things use the 2.4 gig frequency band. Interference and noise are going to weaken the signals that we have for these things. Electrical interference, the proximity to the electrical devices. My student who had his setting under the fluorescent light on top of the refrigerator. Electrical devices can do these things. Advances in wireless technologies have reduced the impact on these things. They're quieter, better insulation, better management of the wireless signals themselves, and then environmental factors, which we talked about a little earlier: lightning, fog, thunderstorms, snowstorms, blizzards. All of those things are going to impact the wireless signals. And when you think, well, it doesn't impact me because it's in the house, we're not really talking about necessarily inside for the environmental factors. The lightning and the fog. Lightning might be, but fog obviously is not going to be inside your building. But if we're going for one of the relays, one of the bridges, it could impact lightning. Yeah, could not, but it impacts the signal just from the what goes on. The electrical interference, the devices that are running certainly could. And when you think about these things, and this is the kind of the not real deep thought questions, you're certainly not going to want to use this in a power station. You're not going to use wired in a power station either, because of the electrical interferences that are going to go on. That's one of the places that we're going to need to put fiber in, because we're not going to have the RFI or the EMI, the electromagnetic interference, or the radio frequency interference, which we're going to have on copper because it'll induce a signal. We're going to have in wireless, obviously, because it's going to affect. If you're in a situation not very far from us, there's some high power lines, high tension lines that go from point A to point B, go across some areas, obviously. If you're too close to something like that, it can cause interference. Different things, different characteristics. What you may need to do is a wireless survey. What kind of impacts do you have? And some of those are going to be, some of the devices are really expensive. Some of them you can buy that won't do as extensive of a survey, but will give you an idea of what's going on. What kind of impact do you have? Wireless, your microwave ovens. There were some early on, some IP cameras that would impact what goes on. What about all of the other devices that are around? What frequencies are they on? What channels are they on? if I change from a 2.4 to a 5 gig, will that help? Now, wireless classes, we used to go do a survey, and we actually found out that they messed up the installation, because the thing that we showed a little earlier to it, the configuration of these things, ours was kind of like this, but what had been configured here, they did like a 1, 11, and then they got another 1 here, and they don't want the overlap with a 6, but put a 6 here and then a 1, so that they did have, and a 6 down here, so that they did have an overlap from one to the other. Had to go in and change the channels that were on. Not a real big deal, but things that you want to kind of pay attention to is the overlap, the interference from one, that will allow degradation of the connectivity. The characteristics, the 802.11 is the standard, and all of the letters after that are the amendments. So the 802.11, 1997, been around for a long time. The original was 2 megabits per second, ratified 97. The 802.11b brought us to 11 megabits per second, introduced in 99, and 802.11g for the 54 megabits per second, 2003. And we'll go down to 802.11a, which was the original 54 meg. It's the 5 gig that we're using. Says it was introduced in 1999. It was, but it wasn't produced until later. And then the question always, at least to me, is why wouldn't you use the 54 meg instead of the 11 meg? But it will be a shorter distance, but that not really probably all that consequential. They didn't really make them. They developed it, but didn't manufacture the 802.11 until later on. The story is that they couldn't get the silicone that they needed in order to make the chip, for whatever it's worth. 802.11n was one of the first big breakthroughs, recent breakthroughs that goes on with it, introduced in 2009. It used both the 2.4 gig and the 5 gig, and we had a big jump in data rate here. We got to 600 megabits per second. It's a high throughput, introduced in 2009. This introduced a concept called MIMO. MIMO is multiple input, multiple output. We've talked about, and let me draw some bad scrawling down here, that we can have now multiple antennas on the devices, and we can have this connection here, and we can have another connection here, so we can have multiple connections instead of a single half duplex connection. We can have multiple inputs and multiple outputs depending on the number of antennas, and it is a function on antennas. We still can only have a single device, a single user and multiple input, multiple output, MIMO, when we do those things. When we get on down to these guys, we can have the multiple user, multiple input, multiple output, and you see that actually we're going to have a 6.934 times the 802.11 AC standard. We're going really fast with these things now. Wi-Fi 6 expected late, whatever. And I think that the 802.11ax is available for these things. I know 802.11ac is when we do that. And it uses we see here the yes, and the AX uses both, but the AC only uses the 5 gigahertz frequency range. The next chart, kind of more of the same, kind of some of the different things here, but 802.11a, same things we talked about, 11a, 11b, 1999, 5 gig, 2.4 gig, 54 meg. The bandwidth, 20 megahertz for these things. The antenna configuration, a 1 and a 1 on each, one on the workstation, one on the access point. SISO is single input, single output. So we're sending a single signal from one to the other, and that goes through 11A, B, and G. The frequency, the data rate changed, but the how many can we have connected didn't change, the 1-to-1, until we get to 802.11n. 2009, it used both the 2.4 gig and the 5 gig, 600 megabits per second. The bandwidth and what it would do, could do, 20 megahertz and 40 megahertz would bond the frequencies or the channels together. And I did that for a while, and then I broke my wireless, and I had to undo that after a while. Let me see if I can get an image here that will show that. Maybe I can and maybe I can't. What the bonding might look like. We can have bigger bandwidths. 802.11ac. We get into an even more sophisticated situation, and I think that I have delete. Anyhow, I'll see if I can find it to show you what it would look like. It's just a matter of what we had from one to the other to go to these things. So 5 gigahertz, 802.11ac, up to 3x3. 4x4 is the number of antennas, so we could have 4 connections and 40 megahertz. And what would happen, it would automatically create these bigger channels back to the from one to the other, back to this. What it would do would now 40, these are 20 meg. What it would do would bond these channels together, so we have a great big bandwidth in here. The bigger the bandwidth, the more data we can put on these things, more data that goes onto it. So it would bond into the 40 megahertz channel to allow us to have the bigger configuration that we wanted to do. And get back to the one that we were on. So then we have the 802.11ac uses only the 5 gig, but it's 1.3 gigahertz, and the channel bandwidth 20, 60, 80, 160, up to 3x3 for the antenna configuration. It's still a single user, but a multiple input, multiple output, where we can have multiple connections from our device to the access point to send data more than one at a time when we do these things. And then 802.11 AC wave 2. This is where we get into the multiple user, multiple input, multiple outputs, that the users don't have to wait for each other. Wireless uses the CSMA CA, collision avoidance, where before you can send, you send a request to send to the access point, to the control device, and then it gives you permission to send. When you send the request, you also tell it how long you think you're going to need the access point. So it then gives you access to the media. You're the only one that can use the media at that time when we do these things. So these, you're established. We're getting faster and faster and faster with wireless. Security is still an issue. Speed, not so much what goes on with these things. And the physical rate here, you can see that it continues to go up. 450, 802.11n, 400, 600, 1.3 gig, on down the line. And then the channel bandwidth, a lot going on this slide. But the over here, the spatial streams, the configuration, we have the receive and the transmit, the different streams that are going on, data streams that are going on the next